director for STIAS since 2019 for the visitors who are coming. We're very pleased that you're joining us in this very exciting presentation by Nigel. It is the first in a series of 3 public lectures per semester. And so thank you very much for leading the way. And it means, therefore, that we shall be able to see you at least 3 times this year. So please don't disappoint me. Welcome, and for the fellows in residence, thank you very much for the support that you're giving to the fellow. But as it is the practice for public lectures, we ask somebody, a scholar from outside of STIAS, to introduce the speaker for the public lecture. And Professor Ma has accepted to introduce Nigel. Christoph, our senior program manager, will handle the question and answers, and also in the process to recognize some of you who are here, as well as colleagues that are on the online. So it's my pleasure then to introduce the introducer. Professor Ma is from Stellenbosch University in the physics department. He studied physics at Nanjing University and at the Institute for Theoretical Physics at the Chinese Academy of Sciences. His PhD in astronomy is from the University of Cambridge. And after his PhD, he did a bit of detours and eventually moved to KwaZulu-Natal in South Africa in 2015, where he became a full professor. But last year, he made another move to Stellenbosch University. And now he's to take up a full professorship and head of astrophysics position in the Department of Physics, as I mentioned. He actively works on radio astronomy, large-scale structure of the universe, so things that big, and many other surveys that he's been involved in and very active. I should also say that Professor Yinze was very, very much involved in the physics symposium that we had in 2022 and worked with the National Institute for Theoretical Physics to make sure that that happened very well. Greatly cited, but I don't want him to compete with the speaker. And he is, I should also mention that he was elected to the Academy of Science of South Africa in 2022. So in that regard, he's a fellow member of the Academy since I was elected last year to the Academy. So it's a pleasure to have Yinze introduce Nigel, please.
Ladies and gentlemen, distinguished guests, it's my great honor here to introduce. Yeah, I should speak here. Okay, yeah. It's my great honor to introduce Sir Nigel. So, Sir Nigel is a STIAS Donald Gordon Fellow, and he is a leading researcher in artificial intelligence. He's a principal of the Jesus College, Oxford, and the professor of computing science at the University of Oxford. And he is a chairman of the Open Data Institute, and he co-founded with Sir Tim Berners-Lee. And in 2009, he was appointed as the information advisor by the UK Prime Minister, and working with Sir Tim Berners-Lee, led the development of the highly acclaimed data.co.uk website. In 2010, he joined the UK government's public sector transparency board, overseeing open data releases across the public sector. He was knighted in 1913 for the service to science and engineering. Sir Nigel has been working for AI for over 4 decades, having obtained his PhD at the University of Edinburgh's Department of Artificial Intelligence in 1984. There is a Department of Artificial Intelligence in 1984. Think about it. That is significant. His first tenured faculty position was in the Department of Psychology at the University of Nottingham, where he established and led a vibrant AI group. He moved to the Southampton School of Electronics and Computer Science in 2000. At Southampton, he researched the next generation of the World Wide Web, WWW, and was the first head of the Web and Internet Science Group. At Oxford, he has focused his research on human-centered AI in a wide range of applications. Most recently, he was asked to lead the setting up of the Oxford Institute of Ethics in AI. With over 500 publications, he has researched and published on topics ranging from cognitive psychology to the computational neurosciences, artificial intelligence, to the semantic web. In 2018, he published the Digital Apes, How to Live in Peace with the Smart Machines, described as a landmark book. He's a fellow of the Royal Society, the Royal Academy of Engineering, and British Computer Society. So now, ladies and gentlemen, let us welcome Sir Nigel.
Well, thank you. And first of all, some thank yous. Thank you, Professor Marr, for your very kind remarks and introduction. And thank you, Edward, for inviting me to STIAS as a Donald Gordon Fellow and for asking me to give this public lecture. It is an honor. Thank you to all of the STIAS staff who work so tirelessly to make all of this happen and to make STIAS such a wonderful experience. Truly, as the website proclaims, a creative space for the mind. And thank you, all of you, for attending this talk, either physically or virtually. Here we go, the first challenge. Yes. And most importantly, thank you to my fellow fellows. This is a wonderful group of brilliant people from so many disciplines, from so many geographies, with so many different perspectives, each with deep expertise, knowledge, and wisdom. It's been a pleasure to be here. For all of 4 weeks, it's already been hugely enriching. So in this talk, it's actually in 3 parts. I'm going to discuss what makes the scientific method so powerful, how it's transformed our world, how it is always work in progress, how it's fundamentally about understanding and managing uncertainty, how it's been informed, enriched, and made possible by accomplishments in engineering. I'll also then talk in the second part about AI, say something about its various strands and recent developments, review the various roles AI is playing in science and how it is augmenting the scientific process. We'll also see that error is a persistent phenomena in our AI systems, and how AI has the potential to be weaponized to undermine science, but also how it can be used to confront disinformation. And then the third part, we'll look at the particular project I'm engaged with here at STIAS, how AI and open data could be used in the inspirational Adam-Task corridor. So 1543 was an extraordinary year. 481 years ago, 2 publications changed our world. The first, by Andreas Vesalius, a landmark work in the field of anatomy, a pivotal moment in medical history. A Belgian anatomist and physician working in Padua University, he produced this 7-volume work, which is renowned still for its detailed and accurate anatomical illustrations. Vesalius's meticulous dissections and observations laid the foundations for modern anatomy. It challenged long-standing wisdom from classical times, from Galen and others. Galen's work had been based on animal dissection, so it corrected many errors that arose as a result of that information, from the structure of the heart to the jaw, from the liver to the muscular system. His insistence on empirical evidence and hands-on research, hands-on observational science, and the use of human dissection was revolutionary. But the Fabrica was not only revolutionizing our understanding of the human body, it also exemplified the spirit of the Renaissance. It blended scientific inquiry with art, marking a move away from reliance on ancient texts and authorities. His work wouldn't have been possible without many other developments. Wouldn't have been possible without advances that have been made during the Renaissance, including artistic developments in literal visual representation and the technical and engineering development of printing and refined woodcut engravings. If we move on then to, hopefully, still in 1543, the same year as Vesalius's work, the Polish astronomer Nicholas Copernicus published, again, a pivotal work in the history of science on the revolutions of the heavenly spheres. His work proposed a heliocentric model of the universe, one in which the Earth and other planets revolve around the Sun, contrary to the prevailing geocentric model which placed the Earth as its centre. His theory was revolutionary. It challenged, again, classical views. It challenged a dominant view of humanity's view in the universe. It was based on painstaking observation. It challenged existing authority. It laid the groundwork for future astronomers, such as Kepler and Galileo, to prove the heliocentric model. A century later, Galileo was formulating his laws of motion, the concept of inertia, again contradicting classical views that believed a force is required to maintain motion. His insights that objects fall at the same rate regardless of mass, his conceptualization of acceleration were all hugely important. His method of systematic experimentation, mathematical analysis, again, consolidated an approach to understanding the world via careful observation, correcting misconceptions, and reproducible experimentation. And his publication in 1638 formed the basis of what later became materials science and kinematics. 50 years later, we have Newton's Principia Mathematica, an extraordinary work that explained Kepler's laws of planetary motion, which Kepler had first obtained empirically. It put the science and the theory into planetary motion, explaining how classical mechanics could describe with exquisite precision the movements of planets, satellites, comets. In formulating his physical laws, Newton had developed and used new mathematical tools and methods. And he revised, in a revised conclusion at the end of the Principia, in a later edition, he acknowledged the importance of experimental work. Now, none of this would have been possible without engineering. Without engineering, there literally would be no science. Through centuries of scientific advance, with its roots in artisans and craftsmen, we provided the means for scientists to measure and observe, for gathering data about the world that enabled a scientific understanding to develop. From Hans Lippershey's eyeglass maker, who developed telescopes and microscopes, through to the wonderful chronometers of Harrison that helped him keep time at a sufficient precision whilst at sea to calculate position, help navigation be more precise. All of this speaks to an evolving set of principles. Now, I hope you won't mind, fellow fellows, if I take some of your images in vain, because I'm going to hold you up of examples of this method. What developed out of these and other pieces of work was a method. As it evolved, it became more than a set of procedures. It became a mindset, a commitment to a quest for truth, grounded in open-mindedness and informed skepticism. It was also built upon the recognition of its own limitations. There was an inherent recognition of uncertainty, the possibility of error, always being a fundamental aspect of the scientific method and the scientific process. So if I look at my fellows here, all of them, I would suggest, are brilliant examples of practitioners and advocates of the scientific method. Faith's work on wastewater-based epidemiology to determine human exposure to pesticides in Kenya. Ramil's work on supercomputing simulations and observations from the meerkat to understand galaxies across cosmic time. Maria's research on controlling stem cell fates to advance skin regeneration. And Thomas's exploration of neuron diversity and their various vulnerabilities in neurodegenerative disease. All results, all recruit the scientific method to help them understand the objects of their study. So, error. Science must always stand on the edge of error because, well, it's empirical. It requires evidence, which is obtained through observation. Those observations can be influenced by all sorts of factors. Those experiments may have limitations or flaws themselves. We must always acknowledge that our data may be variously flawed. The instruments and technology that may be crucial may also have limitations, measurement errors, human involvement. For various reasons, humans may come to their evidence with particular views. We love to imagine that we are entirely free of all sorts of bias when we come to our data, but sometimes error can be propagated. Sometimes people are simply tired. Sometimes people are simply incredibly focused on aspects of the data and don't see a wider picture. The phenomena we're looking at are intrinsically complex. They're uncertain. And sometimes the ethics that we apply don't allow us to do some of the experiments we might think could resolve an issue. So science recognizes the potential for error. It has built-in mechanisms to minimize and correct errors over time. And the method itself emphasizes transparency, replication, peer review, to ensure the reliability of findings. And scientists aim to reduce errors through careful experimental design, rigorous data analysis, and critical thinking. But for all of us working in science, it's a recognition that we could be wrong and that we're able to detect when we might be, or that we're in a process where future generations may improve on what we have achieved. So, back to engineering. With all of the accomplishments, to observe nature, to gather the data, to accurately measure it, to analyze it, generate it, and model it, we are fundamentally dependent on engineering professions and practitioners who build the most extraordinary devices, working in consort, of course, with the scientists. Whether it's Large Hadron Collider, electron microscopes, or the most recent remarkable miniaturized sequencing devices that you plug into your laptop and can sequence biological samples. Or more locally, your recent conference here on meerkat, radio telescopes at scale here in South Africa, which can open up a new view on the universe. Or the remarkable James Webb telescope, millions of miles out there. Absolutely exquisite, audacious engineering, revealing new insights, all of which require computing power at huge scale, which of course all requires engineering. And this is one of the most famous, we'll call it a law, it's really an observation that I like to point to. This is Moore's law. This is a log linear graph. Basically, this scale is giving you a sense of the number of transistors, which is a rough measure of compute power of various computer chips over the ages. And here's from 1970 up to a couple of years ago. The trouble is this changes all the time. Every year I have to add another kind of ridiculous number on the end of this. And having been in the field for quite so long, I can tell you that when I first started, the chips available around about 78, well, they had 68,000. The chips that we now use to power clusters of computing, the NVIDIA newly trillionized hardware company, 80 billion transistors for a single processor. Now, of course, by inspection, you can see that's a 6 order of magnitude increase, 1 million times more powerful compute. With those kinds of changes, and it hasn't just applied to chips, it's applied to memory, it's applied to communication speeds, truly exponential changes, we have been able to realize in AI, and much of what we do in computational modeling, algorithms and approaches that were imagined but not conceivable, not materializable just decades ago. Okay, so what I've talked about so far is the rise of the scientific method. It's aimed to reduce uncertainty, perfect our understanding, always recognizing that it's provisional. There are built-in methods to refute as well as confirm ideas. To get beyond this idea that often is held in the public that scientists parade around in white coats with absolute certainty on facts. That is not how the process works. And I think if we could convey that more effectively, there'd be a lot more, less of an abrasive contact often between public perception of what science is and what science is trying to achieve. I've also talked about the essential importance of engineering, the mutual dependence of science and engineering. So now I'd like to talk about AI, to introduce some of its basic techniques, tools and methods, and to discuss how it's being used in the scientific endeavor. Well, so like so much of what we do in our field, we revert back to Alan Turing, this remarkable individual who in 1936 wrote a paper that appeared in the Proceedings of the London Mathematical Society that literally laid the foundations of computer theory. And then, with a short break to work in the war, building the most extraordinary, helping design the most extraordinary compute engines to crack the wartime codes at Bletchley Park, he moved to Manchester. And in a 1950 paper, in Mind, a philosophy journal, he described the imitation game, also known as the Turing test. He described the possibility of machine intelligence, as he called it then. There's a lovely picture there of Turing in front of the Mark I, the Ferranti Mark I console in 1951. The interface is actually an oscilloscope, effectively. They're looking at signals that give them an indication of where in the process, in the program, they were. But he could imagine in 1950 a world in which compute power would expand sufficiently that you could seriously ask questions around the notion of, is this program exhibiting versatile general intelligence? We'll come back to that. And then I've got a definition there on the right from, well, the coining of the term artificial intelligence arose. We tended to call it machine intelligence in the UK. Artificial intelligence in 1956. The Dartmouth Conference coined the term. It expressed this audacious ambition that every aspect of learning or any feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it. Well, that's a bold claim. The other kind of slightly alarming fact is that the field, as named, is precisely as old as I am, 1956. You can work that out. And the other thing to put to rest is AI is not just machine learning. So it's been around a lot longer than people think. And it's also not all about machine learning. And here are some of the techniques that we have developed in AI over the decades and still developing. It's a large and expanding set of theory, methods, and tools. It's also been pervasive and ubiquitous for decades. Your phones that you carry around are loaded full of the products of artificial intelligence, from face recognition to voice recognition, from the GPS, signal management that goes on in the background. Indeed, much of the shaping of the traffic on the internet managed by AI algorithms. Or indeed, the search engines you all use, or the find me a route to X and Y, the kind of Google Maps experience, all of that, when I began the field, had you handed me one of these supercomputers, I'd have thought we'd essentially solved the problem of general artificial intelligence. Well, we haven't. We've got lots and lots of capabilities that become pervasive, become ubiquitous, and then seem unremarkable, and we move on. They augment us, they help us, but we move on. But back in the 1980s, a dominant approach to AI, the so-called symbolic AI, and this was following on from that idea we saw expressed, which was that you focus on representing knowledge as rules, either in logic or other approaches. It relies on an explicit encoding of knowledge into a computer. It emphasizes the manipulation of symbols to mimic. Well, we kind of imagine we were mimicking cognitive processes. And there's a very trivial little example which medics here will laugh at, but it makes the point. If a white blood cell count is less than 2,500, then you've got a low white blood cell count. Okay, if a temperature is greater than 101 Fahrenheit, you've got a fever. And if you've got a low white blood cell count and fever, then you might suspect you've got a gram-negative infection. And if you've got a gram-negative infection, you might administer penicillin. Now, any real set of rules in medical expert systems or knowledge-based systems, as they call it, would be much more complex than that. They'd deal with uncertainty of particular findings and so have a way of reasoning with probabilities. But the essential elements are explicit representations that capture human knowledge, can be manipulated and used to provide explanations, justifications for the conclusions made. And we built a lot of systems at that time in this way. In fact, one of my favorite, this system was the first system that spin-out company that I was involved in that sold to an American company. And what it would do, it would take this schematic layout, this chemical process here, and give you a three-dimensional layout. It was hard yards to take the knowledge from chemical engineers and the textbooks and describe it symbolically. We were using rules and constraints, structured objects, not least because a huge amount of what an engineer knows is common sense knowledge. It's not in the diagram. It's not in the specification. That when you get this liquid from these containers here to these reactors here, there are no pumps specified. Well, how do you get the liquid there? Anyone knows you use gravity feed. You put one pump higher than the other, but it's not in the specification. It's a piece of common sense reasoning. For all of these reasons, building systems that solve particular problems in this style is hard work. There's always a problem around knowledge acquisition, knowledge management, knowledge maintenance. And you've got to generalize. Once you've got the system for one task, how do you build it to work across many tasks? But these systems were built, they were implemented, they have been extremely usefully applied. And it's not the only success story in symbolic AI. If we look at an approach that uses logic, so-called automated theorem proving, serious mathematics has been proved using these systems. In fact, a solution to the so-called four-color theorem, which is a nice, had been observed years ago, this nice kind of conjecture that no more than 4 colors are required to color the regions of any map so that no 2 adjacent regions are the same color. Hadn't been proved until this machine-supported, very extensive proof resolved it. And there's a whole bunch of results from algebra, from mathematical constants, from knot theory, from graph theory, that have succumbed to this style and approach. However, there'd always been a different way, a different method. A sub-symbolic method. A method where you don't model explicit rules. Rather, you build a neural network. You take your inspiration from systems that are networks of nodes connected together, much as the human nervous system is. You present these systems with large amounts of training data, and they adjust the connections between the various artificial neurons. Now, there are many respects in which, when anybody talks about an artificial neural network, these nodes here, and these links here, analogy is between nerve cells that are connected by axons. But actually, this is an extraordinary simplification of anything that's going on in a real nervous system. But the fundamental idea of connecting nodes by weights, feeding in input, encoding the input on the input layers, and then passing activation weights through each layer, and then making a classification or an outcome decision at the end. And if you're wrong, to go back and change all the weight settings, a process called error correction backpropagation. Again, error at the heart of this very learning method. This has given us an extraordinary range of tools, machine learning tools using this approach. This actually is just a paper from 2017, which showed a system using this style of architecture that could actually take thousands of images of skin cancer and operate at levels that an expert dermatologist would. Okay. Well, it could if your skin pigmentation was Caucasian, which immediately brings you into issues of how you train your systems, how representative they are, have they been tested on a sufficiently wide distribution. And with the increase in compute power and access to enormous amounts of data, neural networks have become extremely prominent in the 2000s. In fact, I'd been working with a very interesting class of neural networks in the late 90s and 2000s as well. This is a little Kepra robot that would trundle around. Its environment has little infrared sensors. And there on the screen you can see a differential equation, partial differential equation that describes, it's taken from biology, it describes how synapses will change their weights if they were competing for, well, in fact, in biology, a growth hormone that is secreted, or growth chemical that is secreted by the nervous system. So you can adjust weights dynamically in real time depending on the input you're getting. Very biologically inspired, had some very nice features, has a lot in common with what is nowadays called liquid neural networks, because it can change the network weights in real time in response to the environment. It can deal with uncertainty and variability. No two of these little robots was exactly the same. The infrared sensors were more or less crummy on some sides and better on the others, or the wheels didn't run exactly at the same rates, or the wear on two sides of the tires wasn't exactly the same. That's the real world, full of nonlinearities. These kinds of systems can learn to account and adapt a little nervous system for the particular robot itself. Interesting learning. But aside from all of that, we have had an absolute explosion of different types of neural network, different ways of configuring those nodes and links, different ways of feeding in the data, different ways of segmenting the networks. A whole plethora of techniques, much of it powered by increasing compute power and increasing amounts of smart people working on this whole area. It's become extraordinarily popular. Computer science has undergone, at our university, it's now the most popular applied for subject at any degree at Oxford. Eclipsing PPE and law and all those other things, computer science. They all want to come and do AI. Well, if this is going out live, I should probably just qualify that a bit. But it's an interesting point. And of course, these techniques are now being recruited to support science in multiple domains, using multiple techniques, augmenting the scientist. And this is a nice example I found of a system that's used, actually, it detects the exoplanets and the gases that swirl around these stars shouldn't obey, well, Keplerian laws, gravitational laws. But actually, if there's a planet in there, they'll be distorted in various ways. You can pick those signals up by attending to particular wavelengths of molecules. And whilst humans find this extraordinarily difficult, machine learning has been trained to identify these particular signals amidst huge amounts of data and noise. And indeed, in a rather lovely example here in this work, to then go into it was the simulation that gave them confidence to believe that what they were seeing was a real signal in the noise. Of course, we can't get out there yet and find the protoplanet, but it's an interesting idea. Or folding proteins, which many of you will have heard of, this 50-year-old challenge of how you work out how proteins fold, thought to be intractable. Used to take years and years of human labor to work out from observational study how a particular protein conformed itself in 3 dimensions. Many of the colleagues here, fellows working here on topics related to aspects of biology, are working with and around these sorts of tools. Gene expression, counting plankton, estimating income, deforestation. I can give you example of these kinds of methods that are being used to help scientists from AI. So now just let's bring ourselves up to date and think about a particular challenge, which is the explosion of what we now call generative AI. All of this stuff we hear about, ChatGPT, for example. What's going on here? Well, in 2022, I wrote the introductory article to the Journal of American Academy of Arts and Sciences, which collected together a set of essays from people working in the field, and a good many of them working on these machine learning and pioneers in the area of deep neural networks. And the last time they'd done an issue like this was back in the late 80s. And the title of my essay was From So Simple a Beginning, Species of Artificial Intelligence. I was trying to point out that just as in biology, that is the closing line of Darwin's great work, Origin of Species. That if you look at AI, it's almost as if we are generating this kind of species tree of different techniques and methods. And some end up going extinct, but others become vibrant, and they populate this whole ecosystem that we find AI to comprise. And one that has become particularly successful is the so-called generative family of AI machine learning, or transformers. The reason it took us all by, I would say, surprise, it was its unreasonable effectiveness. So here, in that book, the afterword in the book was the product, and yet we hadn't yet had the big release of ChatGPTs to the public gaze. They're given a Google large language model, as they're called, a Google large machine learning based architecture. Exam questions from the All Souls exam. All Souls is notoriously one of the kind of really up-it kind of Oxford colleges, and if this is going out live, I've got to be very careful what I say. It's a wonderful college, as we all know, with very tough exam conditions, and notoriously so. And you can see some of them there, you know, is the Turing test a reasonable criteria for achievement of general AI? There is no Marx without Lenin. Does Kant successfully refute Hume's skepticism? And they give these questions to the model, and out would come coherent, entirely reasonable answers. And that started a lot of us thinking quite hard about this extraordinary rush of competence that was starting to appear. They could also write code. These systems, so-called GPTs, or generative pre-trained transformers, they're a method by which huge amounts of data can be ingested. In fact, in this case, almost most of the available internet ingested, and the patterns found that exist between words at very large distances. So you're not looking at essentially a relationship between one word and another. You're looking at huge extensions to work out the statistical representation, in fact, represented in a format known as vectors in very high dimensional spaces. What this means is you can express deep dependencies that would not be available for inspection using traditional methods. And so these systems are able, effectively, they boil down to be able to predict the next most likely word, which sounds an extremely simple job, doesn't it? Except that when you throw this power at it, the next most likely word and the next after that becomes a coherent extended response. And that has been the revelation. And the thing has all been fueled by the fact that shortly afterwards, people discovered that the bigger you made these models, this is essentially how big the models are, they get into the millions to the billions of essentially parameters, or think of them as weights in those neural networks. They get better and better at tasks that you normally give a human to solve, that humans would be more or less good at, and in some cases they begin to exceed average levels of human performance. This was a system called PaLM, which was Google's large language model, which was ingesting a huge amount of data, as you can see. Now, there's just turned into an arms race. So we now have company after company releasing its tools saying, no, this is better. We can pass more exams, we can translate more languages, we can do a better job than you never thought of, and the results are truly impressive. I mean, when you're translating between languages, rather exotic epithets or proverbs, or it becomes really impressive to see how capable these systems have become. They can take it on in one language and emit in another. And we've gotten to the stage now where a recent release, Google's Gemini system, released at the end of last year, begins to show an ability not just to work across text, and many of these models can also work across other modalities, images as well. And I'm going to give you a sense of how this system works by showing you a brief clip. This is not an advert for Google, but it does just show how the tool is now able to augment the scientific process.
Tens of thousands of scientific papers in genetics.
Can you get that? Okay, you can't get that. I'm playing it back. Okay. Okay. All right. Well, she would be explaining. If you go and look her up on the Google Gemini page, you would be hearing her explaining that they built essentially a system to review thousands and thousands of scientific papers. In fact, they took as an example a review paper that had, and actually human beings did this, they took these papers and boiled them down to find the papers that were relevant results relating to a particular aspect of life science they were interested in. And what this extraordinary system is able to do is to take 200,000 papers, read them over a lunchtime, identify those which are relevant in terms of the topics that the review or meta-review is interested in, return them, and then update the actual figures to the new found reality. This is an extraordinary capability, and we'll just let her go through to prove that there was the old figure, 200,000 papers later, and the 230 that were actually relevant, it spits out the new one. Okay. These tools promise real advances, real advantages for the scientist, obviously. And we're starting to think about how the human and the machine will be entangled, whether it's in protein folding, whether it's in predicting chemical sequences. And all of this has depended fundamentally on engineering power. Without the engineering that's gone in the background, we wouldn't have been anywhere close. But I want to just now consider another aspect of these systems. They are not infallible. They can be fooled. In fact, one of the early demonstrations of neural networks had a system confidently claiming that the object here was in fact a bubble and this was a peacock with 99% confidence. Or I put this small image onto a stop sign and it moves from being a stop sign that it could recognize to being, rather worryingly, speed limit 80. Okay. And this is because, and they evolved these, in fact they used an approach called generalized adversarial learning, where they get a system, another neural network, to try and devise patterns that will fool the other one. And in round after round after round, they generate an image that it tries to get the other one to misclassify. After thousands and thousands of epochs, this is the image that will convince the neural algorithm this was tested on that this was a bubble. What you recognize in that, of course, is these systems aren't seeing the world in the way that you do in any sense at all. There are other sources of error. You might be surprised that ChatGPT still can't do sums. I asked it a few months ago what 2,340 times what 4,321 was, and it confidently asserts it's 10,105,140. Now you might think that's a pretty horrid sum to give it. You could look it up on my calculator. What it demonstrates, it's wrong. By the way, it's 10,111,140. In fact, I just tried it the other night and it's almost there. Okay, it's about 200 out. That's not quite what you're after with arithmetic, is it? You would not get a tick in the box. So what you have to ask yourself is why is this? These systems do not have theories about how the foundational elements of arithmetic work. They can tell you what they are, but to apply them. Now, of course, what you might say is, well, you just want to call in a calculator at this point and get it to do those sorts of sums. Of course, what you point to there is an ability perhaps we might see emerge, which is to use these large language models almost as an interface method to pull in other tools that we know work reliably. Some of those good old-fashioned symbolic AI techniques that do their improving, where you want to be confident of the result. You just don't want a statistical approximation. They hallucinate still. So this little leaderboard here is interesting. What it tells you is, on a task where you give a system 800 papers and ask it to summarize them, the best performing system, about 4% of the facts are made up. They're hallucinated. They're not in the original papers. You might think, well, still a good effort. But then you ask yourself, who's going to do the due diligence on all that summarization, okay, ultimately? And how do we kind of iron this out? It is in the nature of these modern machine learning methods that they are statistical approximators, and there will be error in their core. Huge amounts of research are trying to iron that out, but it's just the way it is. The other thing I'm afraid that these systems are being used for is to perpetuate scientific fraud. So some people are using them to write scientific papers, make up the data to go with the scientific paper, and put it out there. What happens in a world where your information base is being flooded with false results or machine-generated synthetic results? There's an effort to kind of detect the fraud, so there's an arms race all the time trying to find out how to get into this, but it's a genuine arms race. So what this all speaks to is a need for ethics and regulation and governance, as well as technical work. A plug for books coming out in May, all good bookshops near you. As If Human, the Ethics of Artificial Intelligence, tries to get to grips with what these rules might be. Right, well, I've been speaking for about 45 minutes. I've got a final third. I'm going to take 10 minutes just to introduce the final part, because we've all seen the remarkable accomplishments of AI, but there are weaknesses. There is the shadow of error emanating from many sources. But nevertheless, these are extraordinary times, and AI, well understood and contextualized with the appropriate data, can be a powerful tool to augment and empower us. So the only noteworthy thing about this slide is the cat. This is Tim and I outside number 10 trying to get data released, and this is Larry the cat, for those of you, he's a very famous cat actually. But we were there running around getting data released and promoting this whole idea that data is a new kind of infrastructure. And then if you release it, you can make applications you haven't thought of emerge. In fact, if you've ever, those of you who've been to London will use Transport for London's apps that get you around, the tube and everything. They're all using data that used to be closed. Transport for London used to think it could write the best apps to get you around London. Now just put the data out there and let the people who innovate around apps do that. The basic insight is that you release innovative flair if you put the data out there. We had great fun releasing huge swathes of data. And had it not been for a few local political distractions in the UK, we'd have carried on. I think we're looking to reanimate that whole project, because not all the data we could have or should have is out there yet. It's still work in progress. So my project here was to think about how can you use open data and these generative AI tools in useful ways. And what more useful way could there be than the Adam Task Corridor, this extraordinarily bold imagining in which STIAS involved with a whole collection of individuals to take this strip of this wonderful municipality and reimagine it, rebuild it, redevelop it in a way that I have to say is extraordinarily impressive in terms of the thought that's got into how you unify these things together. So understand how you bring into inclusion parts of the environment and space and place that aren't used effectively. To imagine new ways of connecting spaces and place and space. And lots of data and lots of documentation. I should say lots of data. A lot of the data is wrapped up inside documentation, which can be a challenge, but not with generative AI, as we'll see. Got to reconcile different needs. I love the fact that this project is imagined in terms of finding your own identity, recognizing that you've got to connect spaces in novel ways, recognizing there still needs to be diversity between these different precincts, a really systems-wide way of thinking about how you develop this space, then how you connect it with the rest of the municipality. Everything is laid down in a municipal document, approved. It's development guidelines. It's a local spatial policy. Really impressive. All the way from movement to services, sewerage to water. Now, what Tim and I were doing in our work on releasing data was also understanding what you need to put in place to manage these assets. So it won't all be about the technology. Sometimes it will be about setting up the right kind of stewardship, the trusts that hold the data, or the right kind of policy to make it available, that it should be findable, accessible, interoperable, retrievable. These FAIR principles, which apply in some areas of scientific data interchange, need to be at the heart of what you build and design. So whilst, yes, this is going to be looking to exploit the technology, it's an awful lot about imagining how we can put in place this new way of thinking about data as a new resource, not as oil, it's a bad metaphor, but as an infrastructure, just as important as your roads and your, well, I'll say the electricity grid, which also shows you both the importance of getting a safe, reliable, maintainable, economic infrastructure. And this one happens to be immaterial. Because it's digital, you can't see it and feel it. Often it ends up being neglected, but it is the most important thing you can build. So, how can generative AI help? Well, even with good old GPT-4 Pro, you can begin to make a chance. I've uploaded a range of documents to GPT and experimenting with the various things it can and can't achieve. It is quite good at summarization. An 81-page document summarized the essential features of what the task corridor is about. It can actually translate materials. It can take that same material and do a passable job of turning it into Afrikaans, or isiXhosa, or isiZulu. It can actually reach into documents that are out there, but hard to access in terms of machine-readable data, and extract the data. So these are taken from very good reports that the municipality produces on the state of the municipality every 4 years, taken from data it collects. Everything from demography to education to health to safety to infrastructure. And this is a very obvious thing to ask, like how is the population growing? Those documents don't have this graph, but it can all be extracted and constructed from the two documents. They even give you some code to show you how to do it. It can tell you about what data assets you should collect. It can begin to tell you about a schema for the information that you might want to associate with the citizen who is enabled and empowered by their data. And another really exciting aspect of this work is to imagine not just using generative AI to help steward and integrate and connect the data together, but also how might we give individuals agency over their own data. And this is very embryonic at this stage, but again, working with my team in Oxford and the work that's underway here, thinking about how we might use new developments in data sovereignty to build on technology to do that. And perhaps finally, the most inspirational part of this, Kayamandi, the informal settlement. A fire in Kayamandi in 2013 destroyed 1,400 informal houses. They started clearing and rebuilding at dawn, and they'd rebuilt 65% of the homes within a week. Within a week. Can you imagine embracing the energy that builds 1,000 homes in a week to the kind of infrastructure we might need to build? Well, how would you do that? How would you do that? You do it by giving them access to the core capability in the digital age, and this is admirable work where literally a broadband infrastructure is being put into the informal settlement. Everybody will get access to that infrastructure and data, unlimited data for R5 a day. If you're going to use these tools to build, collect, to turn some of those wonderful students in the school there who are all now digitally enabled, to be digitally literate, to be digital citizens, curating data, wrangling it, analyzing it, collecting it, being a journalist over it, they need these core tools. So that is a wonderful vision. It's a huge privilege to be here, to be part of that, and I hope in some way the experience and background that I have acquired over far too many years in the field will be of some help and some use in moving that wonderful ambition forward. Thank you.
Nigel, that was simply stunning, and I think you've illuminated all of these, many of these terms that we're thrown with nowadays to an incredible extent for us, and also this final part, bringing it to a very important project close to us. I want to go back to one line, which is at the core of your presentation. It's in your title, but you said it differently in the presentation. Science must always stand on the edge of error. And that, I think, also goes to the heart of what this institute stands for. So thank you very much for that. I wanted to recognize a large online audience, so thank you all of you who joined us. There are several fellows, also a member of the Academic Advisory Council, Edward, and so we appreciate that you signed in. We have some time for questions and answers, and those will be limited to those who are here with us in the audience. So I'm happy to open up the floor. I'll try and identify a couple of questions at a time, and we see how far we go. So first, with the black shirt, thanks.
Hi, thank you so much for a very interesting talk. I'm here. This is something more of a philosophical question, if I may, but at the beginning you mentioned that during the Renaissance, when all the scientific technologies started to develop and there were some breakthrough works, that blending art with scientific inquiry aided scientific progress. Now, in more modern times, there's a general idea that science must be pure logic, and as you talk about AI, you talk about principally using data in a logical way. So my question is, do you think that there is any artistic influence at the moment in the way we develop these technologies? And if not, is there a need for something like that in order for us to improve the error or the way we use it and the way we apply it? Thank you.
Thank you very much. Great question. I mean, I think there absolutely is. I mean, if you look at, well, certainly it's very interesting to see the number of content creators, artists across all areas, from performance to art to music, who are embracing these tools and giving them new contexts of use often that have surprised the people who originated them. I think there's a very, very rich entanglement of artistic culture with the tools. The extent to which the artistic endeavor has informed the development. So it can always sound a little bit cold and logicist, can't it? Or indeed algorithmic, even with our modern machine learning methods. But bear in mind, they have absolutely been trained on huge amounts of creative content. And one of the challenges, of course, is what terms are they getting that creative content on? Are they fair and equitable? And how do we deal with the fact that if we can't tell whether the content is human or machine generated, does that become an issue? And I think one of the things that we are all quite concerned about, for all sorts of different reasons, is this, one of the overriding principles I'm pushing for in the As If Human book, is to say that a thing should say what it is and be what it says. That fundamental should almost be an overriding regulatory requirement. I mean, of course, people won't always do that, but unless you can say that this was machine-generated image, there was a famous early example of a photo that was submitted for a global prize that won. That was actually then the guy said, you know, I did this with an early version of a generative AI program. Yeah, so absolutely, that entanglement's really important. Yeah.
Yeah, so my brain, and I guess everybody's brain, works like in an associative way first. And then later I rationalize things and I go back to my high school physics and chemistry. I don't understand how the brain does that, actually, but how do artificial intelligence networks do that? I imagine this is very important, because if you train things on large data sets, and they don't know about the fundamental laws of physics, chemistry, or biology, or medicine, you would go completely wrong, potentially. Is there a mechanism to do this, which may help us understand how my brain works?
I'm not sure about yours, Hans. I mean, that may be well, it is unique, of course. That's the great thing. We're all running what we think of as, you know, the same kind of, but we're not. We've got these beautifully adapted and carved out neurologies which are precisely suited to your body, to your developmental history, to your intellectual history. So we have the general initial conditions, but we develop a little bit those little robots with my biologically inspired neural network program. You build a neurology that suits you. Human associative memory, I mean, the associative principle has been a very long-standing one in psychology. It's a really important one. And of course, you can find it in various parts. You can look for it in various parts of AI architectures. You can argue that effectively there's some of that in vector embedding. When you look at these very high-dimensional spaces where words cluster together, you can say, well, there are associations in there. Of course, the interesting thing about that is when there are innovative associations that move you to think differently about, or across modalities. If you think about the associations that are now present in these systems that do text to image, they are associative in some sense. In fact, the mappings are explicitly associative. So there is a lot of associativity going on, but I think, as with the appeal to it's a neural network, it's still a long way short, one suspects, of all the associativity principles. I mean, I'm not even sure it could be described as one thing in the way it's implemented in even your brain. Yeah.
So thank you so much for the presentations. I also learned a lot from your presentation, especially from the history. But I'm still having a question, or let's say, maybe it is a bit out of the scope. I'm not sure, but it is related because most of the models we are using now rely on the availability of data, and you mentioned it, especially that's why your project about open data. But in some scenarios or settlement, we don't even have data, especially in part like remote or rural areas and so on. And sometimes it is very difficult because, you know, the reality conveyed by those models are not really the same what people are living in those areas. And I would like just to know if, from your experience, you have an idea how this problem can be, let's say, efficiently solved. Because one part we have the difficulty, the lack of means, because you would like to produce data, that means we have the infrastructure that we need to build, we have the capacity building also from people to create, but also to annotate also those data, because we can have the data, but we don't have the information related to those data. So, and this is, for me, it is a real challenge, and I'm still wondering how this problem can be maybe not solved, but mitigate in the current era of generative AI we are living in presently. Yeah.
It's a great question. And honestly, two things enabled the modern era of AI to be possible. One is compute power, and the other is huge amounts of available data. That available data was curated and pulled together at significant cost, and with a very early image set that was put together, AlexNet, was the resource that was used by the image labelers had been put together at huge effort, you know, heroically put together. The web gave rise to connected text at scales that were inconceivable, but not everywhere, not evenly. So as you say, you know, some languages, some literatures unevenly represented, some languages with an oral tradition and a written tradition. Where's the data for that? In other environments where everything from mortality data to, you know, service provision is patchily available. And there was a very, very interesting presentation at our AI summit, at our Open Data Summit last year, from an activist working in Kenya who said for areas of female public health, there was simply no data. If there's no data, you weren't in the problem. You weren't even recognized by government as an issue. So I think that's a great question. How you backfill it? Well, it won't be one single solution. In some cases, it will be actively promoting initiatives like build your data infrastructure. Just invest in it. It is as important to you as your roads are. If you don't have it, work with those who know how to. You can sometimes have a first mover advantage. The other thing is that not always in the most remote places, but the pervasive nature of these gives us an ability to collect data in a way we've never been able to. With voice activated systems, with the multiple sensors on these devices, we now have effectively millions of potential barometric sensors to give us kind of, and efforts to recruit sensing at scale, which attaches to the citizen, are another way forward. But there's no single way, and it takes effort, and it takes a degree of curation, and sometimes it takes people who just care passionately about getting this representation. And sometimes when you have the data, it's not very good either. Or it's completely framed in a way that excludes or doesn't include. And some very good writing on this from a number of sources who are pointing this out. I mean, one of the most remarkable is it's a book called Invisible Women, and actually points out that in almost all industrial design, in lots of architectural work, in pharmacological trials, the male is the assumed data set. Strength, size, metabolic behavior. Completely extraordinary, but true.
Thank you. I wanted to add one comment for our online audience. You're welcome to type any comments and questions that you have into the chat box, and we'll make sure that Nigel gets them. Or we'll feed them to ChatGPT. Yinze was first.
Yes. Sir Nigel, wonderful talk. And I remember a few years ago when I read the book Homo Deus by Yuval Harari about the future. He said once in the era of AI, etc., the powerful machine will replace half of the population's job, will make half of the human being completely useless. And I want to hear, I mean, that would be a pretty chaotic, society. So I want to hear your comments on that.
There are very differing views on this, and I'm afraid I'm of the camp that observes that humans are extraordinarily creative about inventing new things for them to do that they get paid for. Okay, from social influencers to personal health trainers. You know, there are entire significant parts of our labor and activity that we imagine and create. There's now a new class of occupation known as the prompt engineer. You know, there is. So I am not nearly as pessimistic. I also think that there'll be a huge need for human content creation. We've kind of imagined the machines will do this all for us, but we already have some indications that if the machines are trained on the data they generate themselves, there's a phenomenon called model collapse, which is that literally behavior becomes less interesting and, in some cases, perverse. So I think that about every 10 years in the 40 years of AI experience I have, I actually collected a set of covers from the German magazine Der Spiegel. And about a 10-yearly episode, there's a front cover that says, the robots are coming for your job. You know, manufacturing will disappear. When Kasparov was beaten by Deep Blue, all the jobs are going to go. And actually, strangely enough, will all the lawyers disappear because of AI? I'll take you a bet on that. Okay.
Thanks for some confidence. Next was what? Yes.
Hi, thank you very much. This was very insightful. I was fascinated by the idea that you also talk about now in this answer about how errors can prorogate in a system in which we let like data and information generated by AI, which have fault in themselves, then we let them into science and then we build our science out of that. And you related that to the ethics of dealing with AI, but I mean, if we managed and if we let this data and this information get into the scientific system, does it mean that our scientific system has failed? Does it mean that the peer-reviewed system is not working? I mean, how much of the risks of AI today are linked to certain mistakes or faults that are already present in our society?
Well, look, I mean, that's a really good observation, because I think we all know, those of us who work in these fields, is just what the extraordinary pace of change is. You know, Rickard sent me a paper of a new breakthrough in a machine learning architecture. Well, it's been around for a while, but the latest evidence of a 2-day-old paper. This stuff is moving fast. People are actually now publishing on archive. They don't go through peer review. They simply take a view that it's clicks that'll win. You know, the stuff that wins is the stuff that gets paid attention to. And I think we're going to be rethinking the whole process about how we triage, deal with quality control data that's going to be released at these scales. There will need to be new, I think, compacts, new understanding about what evaluation looks like, how we can be sure that we are not just falling into captured by a particular set of increasingly non-representative data, for example, or data that doesn't have interesting distributions at the extreme. Again, one of the very interesting things that we know from science is that there's lots of interesting variety at the ends of distributions. Bob May, very famous ex-president of the Royal Society, did some very interesting work on this, that these things may be low frequency, but they can be hugely important. So, great question. I don't think we have all the answers, but I think our minds need to be on it now. Yeah.
Yeah, Nigel. Over here.
Sorry, Bob.
Yeah, so great talk. And your example with the arithmetic got me thinking about something, and that is that, is it possible, or what do you think, are people working on the idea that there can be some quantification of the uncertainties in these sort of generative models? And so you can get ChatGPT to give you, say, well, I'm 38% confident in this answer, instead of.
And in fact, that is exactly a way that this is going to go. It's just that I think for certain sorts of requirement that won't quite do. You want to know with rather more like 100% confidence. It's why I think there's going to be this space for hybrid architectures, so that when I design my circuit boards or when I design USB drivers, of most unlikely of things. A set of formal software verification checkers are used that use theorem proving techniques, and they're closed under deduction. You know, if this returns a clean result, you've got an absolutely bulletproof design. And I think there'll always be this tussle between where you're prepared to tolerate a degree of uncertainty, where the error bars are. Where some people say, actually, it's a desirable thing. I mean, there's also a line of thought that says sometimes noise can be helpful in kind of keeping systems from too much lock-in, and the view in which you say, no, this is something I absolutely require, mathematical certainty on. Yep.
Thank you. We have 4 names in the lineup at the moment, or person with the mic at the moment, right at the back with the light green and with the white, and then I just saw Gia as well. Yes.
Yeah.
I was just wondering, by the way, if AI could be of any value in finding the best life partner.
Of course. It's a great question, and of course has been ruthlessly monetized to that effect. My daughter found her. No, I shouldn't say that. Well, she wouldn't mind me saying. She'd absolutely said, all of these kind of dating apps are using essentially matching methods, recommender engines that are. You can argue about whether is this genuine AI or just some reasonably straightforward statistics 101. But of course, yes. Great question.
I am a lawyer, so my demise is imminent. I want to ask about the ethics of the industry thus far, particularly in the release of things like ChatGPT. Are we firstly in an AI summer, and there's now this, beauty contest amongst all these companies to drive investment to them, so we're getting these fantastical stories about what it does and its abilities and so forth. And then, as part of that race, was there this rush to release things to the public without any consideration of the consequences for things like education? Now schools, universities have to deal with the mess of dealing with assessments that we are unable to sometimes assess with credible certainty about who's produced this. So what moral responsibility was there? And after the fact, leaders in AI and you know who they are, sort of are now much wailing and gnashing of teeth and how they regret their life's work, etc.
Yes, I do. Well, I don't regret my life's work, not yet anyway. Look, I think that the Bletchley AI Summit was quite an interesting example where it was a sincere effort to get people together and convene people to have a conversation about AI. There was a lot of talk about risks at that. And actually, some people thought there was a lot of shroud waving going on. In fact, it was all about existential risk. You know, they're going to wipe us out and all the rest of it. Whereas the harms might be much closer to home. They might be much more immediate. And how are we going to deal with those? So the deployment of AI and disinformation in the upcoming elections across the various democracies that are envisaged in the next 18 months. I mean, huge issue there. The use, as you say, of, in fact, Gemini, great, very interesting developed piece of capability, has just pulled its ability to generate images of people because of a toxic piece of imagery that was generated when somebody asked it to generate a picture of people in Nazi uniforms, okay? And it actually, in an effort to be diverse, populated those individuals across a whole range of demographics, you know? And so you had these the kind of issues of what do you do in that situation where you're trying to kind of balance ethical consideration with the fact that these systems are in some sense going to surprise you. We don't know all of their consequences. So is it responsible to deploy? In fact, you know, some of the large platforms have said they deliberately kept their releases back because they were evaluating them. They didn't want to put them out there. I happen to believe in some cases that was the case. But then as soon as competitor X does, the other company feels it has to respond. And so we are in a bit of an arms race on this. And it is important that we are developing rules of the road that talk about what should be evaluated, what the safety considerations should be. What are these organizations going to be asked to regulate themselves, or would we rather invoke other forms of regulatory power? And then you get arguments about whether the EU AI Act is the right way to go, or the US AI bill, or a UK regulator-based approach. All of that is in play, but we've got to have this right at the front of our minds. If you talk to people at these companies, they will say, yeah, of course we want to be ethical. We don't want to do harm, but sometimes the things that arise weren't exactly as anticipated, you know. And with the experience of, for example, some of the unfortunate effects of social media, we should be very thoughtful, I think, about deploying this technology. But that's not to say not, because as much as this tool might be a challenge in an educational context, it's a huge potential facilitator for hard-pressed teachers. The fact that you could all have a personal educational tutor could be an extraordinarily liberating. So it's under what terms, what conditions, what oversight.
Thank you. We'll have two more questions with the white and then Gia.
Thank you so much for the talk. It was very insightful. I'm also a lawyer, so my question is more on the ethical side than the technical side. But I want to come back to the data that we talked earlier about. And I like the way how you described the data as infrastructure instead of this analogy that we've always heard, data as the new oil. And I'm interested that for me there's this contrast in data with when we look at the infrastructure. On the one hand, we want open data and we want lots of data available on different communities, and we want people to share their data, and it's in line with our spirit of Ubuntu, because I am, you are. And so on the one hand, we want that, but then we also have personal data, and we have protection of personal data. And you spoke earlier about to give someone sovereignty over their own data or data agency. So how do we find a middle way between those? Is it either or is there a middle way between those two?
So I'd refer you to the Open Data Institute's website, we've got their whole set of material where we've developed this idea of what we call the data spectrum. And on the one end of it, there is fully open data, open data that can be shared under an open license. And as you move across the spectrum, you move to data that is shared perhaps under various terms of restrictions. At the far end, there is data that is deeply personal, has all sorts of security implications, may only need to be viewed by a very small number of people, possibly, where n equals 1. But that spectrum from very closed to open is a set of conditions you have to deal with, that your terms of engagement, the licensing, the way in which you build architectures to manage it, where you put privacy-preserving machine learning, for example, where you can actually reason over personal data but not disclose details about the individual. The whole set of technologies, as well as, I think, governance principles we need to develop. It isn't one strain, data isn't one species. What I'd like to think about is that the bottom layer, the broadest foundation, should be your open data assets, which is a commons that is held to help innovate and support and promote a whole range of services. And much scientific data is like that. But of course, there'll be other types which are more cautiously shared under commercial licenses, perhaps shared by a collective who've brought this information together, or data that is genuinely important but too sensitive to allow out. I mean, famously, we did some work with poaching, where GPS tracking of endangered species is a highly sensitive form of personal data that relates to, well, you can imagine. And yet some of that data can be used for other purposes in conservation, where you want to have access to it perhaps after the fact in different contexts. So I think we have got machinery to deal with that comes from areas like health and public health. And I think, again, the law has many different ways of conceiving contracts or trusts that can hold these things under different conditions of shareability.
Thank you for this great talk. And as you said, we humans are characterized by being hugely creative and innovative. And of course, the development of AI is hugely creative and innovative, but the AI itself is not innovative or creative. Trained as it is only on past data, past ideas, past methods that are already there. So if we start to rely very heavily in research and education on AI and the augmentation that we can get from that, do you think that it can put, dampen and put a wet blanket on breakthrough research, innovations, because we rely very heavily on what has been done in the past?
Well, I mean, again, it's a very important question. I think there are those who have always worked in AI. AI creativity is a subfield, and people have worked on it actively, wanting to find ways in which you can provide some of the meta level, the higher level tactics, heuristics we use to discover new information. This has been done in mathematics, trying to find whether there are ways in which you can point and help these systems develop new concepts, novel concepts. I think you're seeing it in areas of structural biology where new structures are being proposed that did not exist in history, did not exist in the past training set. So there is, in, I think, generative AI, a possibility of new content. I think the thing that's more challenging is often the breakthrough sometimes comes in science through a reconceptualization, a reimagining, and people will argue about whether it's inevitable that, at this point when relativity replaced classical mechanics, it's going to happen anyway, but there is this idea of what does it take to reimagine actually the context you're in fundamentally, and do our machines have that capability? And that's an open question, it seems to me, but certainly intermingling, entangling the human scientist with these systems, particularly as they become, in a sense, these conversational provocateurs, could be a really exciting new episode of collaborative human-machine development. And we've seen it in a very interesting area, chess. Chess, where everybody said, by the way, well, all these people doing chess will be out of a job. Kasparov's beaten by Deep Blue. Who wants to play chess now? Just because a machine can play it to some level no human does hasn't stopped people playing chess. They still enjoy it. In fact, they now have hybrid teams where they combine together. In fact, they've revealed new strategies and new forms, and this is true in Go, as I understand as well, where new ways of thinking about the game have evolved. So that entanglement, I think, is one of the great opportunities, and it's why often when I talk about AI, I think the better framing is augmented intelligence. It's because we suddenly run off with this idea that they will wake up and want to put away with us, and I think we're some way from that.
That is very exciting, and actually, you know, whichever directions AI will take us in, we are, and you in your career certainly have been living through and will be living through very exciting times. Thank you for bringing all of this to our greater understanding, and thanks for all the wonderful questions. We're pleased to invite you all to a reception outside. Let's have a final applause.